cosine theta over theta. All right, we can actually use that limit we already know of sine theta over theta is equal to 1. Okay, we just have to manipulate this. Okay, and so there are, the way we're going to do this uses Pythagorean identity of trig, which one of the Pythagorean identities for trig was that sine squared of theta plus cosine squared of theta is equal to 1. All right, at some point I will do either a video lesson or point you to a video about identities. I just want to show you this one. Probably will not test you on this one.
When do you think our test will be?
Great question. The test is probably going to be next Thursday.
Okay.
We got two more lessons to go through. So that should be finishing up today, and hopefully Wednesday we'll review. We might go into Friday and then review Friday/Tuesday. Didn't want to give you a test on Tuesday since you'll be taking the ACT that morning. I think that would be kind of mean of me to say, hey, I know you've just sat down and taken a test for 3 hours. Let's test. All right. So we can manipulate this one by getting it to be a Pythagorean identity. All right, because if I multiply the numerator and the denominator by 1 plus cosine of theta, all right, well then the numerator becomes, when you FOIL that out, 1 minus cosine squared. And the denominator has the theta, and then also has the 1 plus cosine theta. All right, so we can actually, that top part, that numerator, is actually just this Pythagorean identity just messed around a little, okay? Because if you subtract the cosine squared from the left over to the right, you end up getting that sine squared is equal to 1 minus cosine squared. So I can actually replace sine squared. And we still have our denominator. All right, and doing that, we can now break our fraction up into parts that we know the limit of, and then parts we can evaluate the limit of. All right, so I can take one of these signs up top, since it's sine squared. I can break those up and have sine of theta and sine of theta separately. All right, and then the denominator, I'm going to split that up by putting the theta under one of the sine thetas, and then the 1 plus cosine theta on the other. All right, so when we evaluate the limits of each part of these separately, the first one, the limit of the sine of theta over theta, that's just equal to 1 via what we've already memorized. All right, and then the other fraction, I can actually just substitute in there. So we end up getting 1 times 0 divided by 2, so we end up just getting 0. Okay. Yeah, I'll show you that, but I will not test on that identity. Yes.
On the test, when you're like looking at our scratch board, you know how you write the limit of theta is going to 0? Would it matter if we like don't write it or write it?
As far as writing the limit, you do need to write the limit all the way down until you evaluate the limit.
Oh, okay. So for like the last 3 lines there should be a limit.
Well, starting right here, I evaluated the limit. So once you start evaluating the limit, the limit goes away. Yeah, when you plug 0 in, when you get to that step, you can leave the limit off. But when you're doing all the manipulation, in order to be able to plug the number in, you need to have the limit. I know it's annoying to write that every time, but so that we're not saying things are equal that are not equal. That is one of the things the AP tests will get you counted off for if you don't. If you write, hey, this equals to that, and they're not actually truly equal. All right. So let's go back to some previous examples. All right, this one right here. Limit of x times cotangent of x is probably on the back of the first page. All right, those two that we talked about that, hey, we could not do those at that point. All right, but now that we know that the limit of sine of x over x is 1, we can actually do these. All right, you have some different work there. All right, so you could actually break this apart into x times, and cotangent is cosine over sine. Okay, in the lesson, remind me, I'll tell you the identities that you do need to know. All right, so if we do a little bit of manipulation, all right, we can turn this into the limit of cosine times x over sine x. Okay, since we're multiplying two fractions, I can switch the numerator and the denominator. We still have something. Because if I multiply it back together, I'd still have the exact same thing. All right, I'm good with the cosine. I can plug in 0 for cosine. All right, but I don't know this one right here, x over sine x, but it's very, very close to being sine x over x, yes? All right, but it is a different equation. All right, but I can rewrite that, okay? Using this little trick right here. I'm going to rewrite x over sine x as 1 divided by sine of x over x. Don't usually do it this way, but basically we're just using the fact that how do you multiply fractions, or excuse me, divide fractions. Keep the top and multiply by the denominator. All right, so basically we're doing that just in reverse. Okay, so that I can get this x over sine x to flip over. Yes. Well, the cosecant of 0 is undefined, so it wouldn't really get us anywhere. Our whole thing is, the reason I'm doing that, yes, 1 over sine is cosecant. All right, but I don't know the limit of cosecant of x times x. But I do know the limit of sine of x over x. All right, but when flipping it over, well, the limit law says, hey, I can find the limit of things that are multiplied and divided as long as they all exist. And so really what's happening here, you don't necessarily have to write it out like this. You have the limit of the cosine of x times the limit of 1 divided by find the limit of the sine of x over x. Which now I can evaluate each one of those individual parts. All right, the cosine of 0 is just going to be 1. The limit of 1 is also just 1. All right, and the limit of sine of x over x, according to what we know, is also 1. So we did all that work and that manipulation, and we got the answer of 1. Which I don't know about you, to me is always a little disappointing when you work a problem out and you get like 0 or 1. In some ways it's like, okay, at least it's a number. Yeah. Yeah, you get that weird fraction, that's also horrible. You get 0 or 1, it's like, yes.
When should we do the thing where you put the limit on like each and like fourth step you put the limit on each one?
Yeah, what about that?
Like when do we know when we should do that?
When I've broken it apart into pieces that I can find the limit of. And you could actually, if you're looking at this third step, you could actually probably go straight to 1. Okay? Because I'm assuming you can probably do maybe this in your head. If you know your trig values, cosine of 0 is 1, limit of 1 is 1, and then this part down here is one that I know is also 1. So you can probably go straight to your answer from there. I'm fine with that. All right, one other one that uses the same type logic, we have the limit of x squared times the cosecant squared. All right, but I am going to use that reciprocal identity. I know that the cosecant of theta is 1 over sine theta. And so I could rewrite this as the limit as x approaches 0 of x squared over sine squared of x. Okay, the reciprocal identity extends if you have the trig function raised to a power. All right, in the case you hadn't seen or forgotten, sine squared, written like that, is really what we're saying here is the sine of x, and then that whole function squared. Somebody asked me that the other day. Make sure we know that. Having that exponent right after the trig function is just kind of shorthand, so you don't have to write as many brackets. All right, so I can actually then separate it. Since it's x squared, which is x times x, over sine squared of x, which is sine of x times sine of x. I can break that apart into x over the sine of x times x over the sine of x. I often put parentheses around the argument of the trig function, just to be totally clear of what's inside the trig function. If you just wrote sine x, you're good. All right, but if we do that same trick we did on that last problem, okay, we can return both of those into 1 over the sine of x over x. the limits of those as x approaches 0 are also 1. Then we get a whole bunch of 1s that are multiplying and dividing, so our answer is just going to be 1. Alright, questions or concerns on those? Alright, last thing we need to look at these notes. We go to the next to last slide. Alright, this came from the AP website. Alright, so this might be how they would test it. Okay? Let f, g, and h be the functions defined by f of x is 1 minus cosine over x squared, g of x is x squared times the sine of 1 over x, and h of x is x squared over tangent of x for all x not equal to 0. All the following inequalities are true on the interval between negative 1 and 1 for x not equal to 0. Which of the inequalities can be used with the squeeze theorem to find the limit of the function as x approaches 0? A lot of words there. Okay? So make sure you focus on the words that are important. Okay? It says, which of the inequalities can be used with the squeeze theorem? Right? This question does not ask you to find the limit of f, g, and h. Okay? They all might have an answer. It's just saying, hey, which one of these can I use this squeeze theorem with? Right? And so I know for f, g, and h, it told us that all these following inequalities are true. So f, g, and h are all squeezed in by functions. Okay, they each have a function on the bottom and a function on the top. Alright, but the only thing we really need to check for is that last part of squeeze theorem. Okay? It has to have one on the bottom, one on the top, but what do we know about the limits of the bottom and top equations? They have to be the same, don't they? They have to be equal. So all we really have to do is say, hey, what's the limits of each one of these and see which one we can actually use the squeeze theorem with. So for f, we say, alright, well what's the limit as x approaches 0 of 1/4? Well, that's a constant, so that's just 1/4. Alright, and what's the limit as x approaches 0 of x squared plus 1/2? Again, easy plug in. 0 squared plus 1/2 gives us 1/2. Alright, since those are not the same, we cannot use squeeze theorem on number 1. We know our answer is probably going to be between 1/4 and 1/2, but we don't know exactly what it is. Alright, what about for Roman numeral 2 down there? They're both what? They're both 0? Alright, so since both of those limits of negative x to the 4th and of x squared, both of those limits as x approaches 0 are 0, then yes, we can use squeeze theorem on Roman numeral 2. Alright, what about this last one? We get this horrible 1 over the absolute value of x. I'm not exactly sure what that one looks like. We could do it.